Clusterization of AI-synthesized voices using bispectral analysis and dimensionality reduction. Hi, my name is Aline, and this is my project for the machine learning course taught by the Professor Alexandre Simões, and it's part of my master's degree program at São Paulo State University. And here is the plan for the presentation. I'm going to start showing an overview about Deepfake. Then I'll show you our dataset. I'm also going to talk about the bispectral analysis and how it can be useful to identify if the speech is fake or not. Then I'm going to show what are the features I've extracted from the dataset and how I used a dimensionality reduction technique to plot the features as a 2D plot so we can visualize the clusters. And finally, I'll present my results. So let's start with an overview about deepfakes. Deepfakes are realistic media created by artificial intelligence. What I'm showing here are two of many possible deepfakes that are to create videos or to manipulate them. The first is the creation of videos mimicking individuals' voice and movements and doing things that were never really done. And the second is that we can easily manipulate an already existing video. And as we can see here in the right, the person was completely removed from the video. As the deepfake technology advances, the generated media becomes almost indistinguishable from real media. Let me show you, for example, here, this video where we can see Jim Carrey as the Joker.
Great. Did you bring it with you? Arthur, last time I asked you to bring your journal with you for these appointments. Can I see it?
This was entirely done using neural networks techniques that, and of course, Jim Carrey never played as the Joker in real life. If you want to watch the full video, you can access the link I provided here, the slide. Okay, these super realistic media are impressive, but at the point that it's difficult to say if something is real or not, deepfakes could potentially also be used for harmful intents, as this example that the Wall Street Journal reported last year when fraudsters used the voice cloning techniques to impersonate a chief executive's voice and ask for money transfers. So, as we can see, the fact that the technology is becoming more realistic may also create some problems. And here in this project, I've worked specifically with deepfake audios, and I attempted to use some techniques to try to differentiate what is real voices from cloned voices. Firstly, let's see how the dataset used in this project is structured. The dataset is made essentially of two parts. The first is a set of speeches I've downloaded from YouTube. Each audio has 10 seconds, and I used 15 speeches from Obama and 15 from Hannah Fry. The second part are AI synthesized voices. I used a system called transfer learning from speaker verification to multi-speaker text-to-text speech that you can see here in the yellow box. This system receives as an input a text, so you can write what you wanted the cloned voice to say. And we need also to input an audio file that will be our target voice. I've used each one of the real speeches as input, So I've generated another 15 Obama speeches and 15 Hannah Fry speeches, but at this time the media are not real. I've put some examples here so you can listen how they look like. On the right is the synthesized voices here from Obama.
The computer is talking like me.
And here's from Hannah.
The computer is talking like me.
You can see that AI really catches how the speakers talk. So now I'll show you this technique I've used to extract the features from the audios. The bispectrum represents the higher order correlations in the Fourier domain. So we've converted from time domain to frequency domain and applied these higher order correlations to our dataset. The bispectrum formula is this, where B is the complex valued bispectrum quantity, Y denotes the Fourier transform of the signal, and omega 1 and omega 2 are the harmonics. Given that the bispectrum is simply a complex number, we can see it as a magnitude component and a phase component, as I shown here in these two boxes. Here at the bottom, we have what is called the bicoherence of the signal. It is a normalized version of the magnitude, and when we do this, we get a range of values that goes from 0 to 1, and that is easy to compare. Okay, so why do we care about these higher order correlations? Well, I've told you that the synthesized voices are becoming almost identical to real speeches, but actually it seems almost identical to our ears, but there are some features that are not necessarily audible, but can differentiate them. For example, these higher order bispectrum correlations that we saw, they are not typically found in human speech, but it is present in synthesized voices. As I shown here in the image, here the bispectral magnitude and phase are shown for 3 speakers. The first one is the real, and the other 2 are synthesized voices. And as we can see, there are patterns not present in real speeches, and these synthesized voices have much more correlations present. So let's see how we can use these values as features for our clusterization. Okay, little recap. We've downloaded the YouTube speeches and we also created synthesized voices. We then generate the bispectrum magnitude and phase for each one of the speeches from our dataset, including real and fake audios. Now, we're gonna use some statistical tools to create 5 features representing each audio file. The features are the average, the standard deviation, and the maximum value of the magnitude, and the average and the standard deviation for the phase. We'll use now the dimensionality reduction to try to transform these 5 features into 2 features. To make this dimensionality reduction, we'll use a technique called UMAP. The UMAP constructs a higher order graph representation of the data and then optimizes a low dimensional graph to be as structurally similar as possible. Here on the left, we can see these points as if it were a dataset. The UMAP uses the simplices to try to find the relationship between a point and its neighbors, and it uses weights to say if the connection is strong or weak. After this, we can see here on the right, it plots the data showing the overall topology of the data. it kept the neighbors next to each other. So we applied this technique to our data set of 5 dimensions to try to transform it to 2 dimensions. So we can easily visualize the results, and we can see if we can separate what is real from what are synthesized voices. Finally, here I show you the results we get. We vary the UMAP hyperparameter to find the different clusterization results, as you can see here in these small plots. Yeah, even in this reduced dimensional space, we can see that we've got kind of 2 separated clusters, one for real speeches and one for synthesized speeches. Yeah, there are some overlap, but we can most of the time say if the voices are from fake or the real group. Also, interestingly, we got some fake speeches classified as real, so we did not catch the difference between them, but we did not get a real speech classified as fake. It's because the real speeches did not have that patterns present in the fake speeches. That's it. Hope you have enjoyed, and thanks for watching.